My name is Vishal Nedungadi, and I will be presenting our work on MMEarth exploring multimodal pretext tasks for geospatial representation learning. As we look at this ASA image showcasing multiple satellites, it perfectly aligns with the core ideas behind MMEarth. In remote sensing and Earth observation, we often face scenarios where ground truth or label data is scarce. The abundance of satellite imagery provides a lot of unlabeled data that can be used to learn meaningful representations without relying heavily on annotated datasets. This creates an opportunity for us to align all this data automatically. Through this work, we study how multimodal pretext tasks impact representations. We start by first creating a global multimodal pre-training dataset. We sample data at 1.2 million locations, which is at the scale of ImageNet. The data is balanced across biomes, and to account for seasonal variance, we collect data throughout the year for 4 years. Each tile represents a 1.2 kilometer by 1.2 kilometer box at 10-meter resolution. Hence, this corresponds to 128 by 128 pixels. At each location, we collect 12 different modalities, which includes both sensors and map products. We group the modalities into pixel level and image level modalities. The pixel level modalities consist of Sentinel-2, Sentinel-1, Aster elevation map, ETH global canopy height map, dynamic world land cover map, and ESA land cover map. The image level modalities consist of the biome information, ecoregion information, Era 5 temperature and precipitation statistics, geolocation, and the Sentinel-2 acquiring date. We evaluate all our models on the GeoBench downstream tasks based on Sentinel-2. GeoBench provides harmonized subsets of the original datasets with comparable training set sizes and balanced class distributions. Prior work on masked image modeling has shown its tendency to learn input representations very well. As opposed to masked autoencoders based on vision transformers, we instead extend the ConvNeXt V2 approach that makes use of a fully convolutional masked autoencoder. Note that we are interested in learning an encoder to interpret optical satellite images, and hence the input is always Sentinel-2. We extend a standard masked autoencoder with multiple reconstruction tasks, one for each modality in our dataset. Given an input image, we mask out 60% of the patches, and this is passed on to the encoder. With the use of masked tokens on the output of the encoder, the decoder then reconstructs each modality. We make use of a separate decoder for each modality and make use of shallow decoders to learn better representations. We evaluate our model by fine-tuning and linear probing on various downstream tasks. The baseline is with our model pre-trained on ImageNet. We show that in-domain pre-training with only Sentinel-2 as input and output already improves the fine-tuning and linear probing results. When using all the modalities as additional pretext tasks, we show that adding multiple modalities improves the representations for downstream tasks, especially for linear probing. To test the few shot capabilities of the model, we linear probe on smaller subsets of the downstream tasks. The results, as seen by the orange line, show that multimodal pretext tasks improve representations for low data scenarios. When comparing our model to prior work, we find that our multi-pretext masked autoencoder performs similarly even with a small encoder. We run another experiment with 2 versions of the dataset. First, we create MMEarth 100K, which are 100,000 locations instead of 1.2 million. We find that fewer locations deteriorate performance. We then create MMEarth 64, which is the original data, center crop to 64 by 64 pixels. We find that models trained on smaller image sizes works on par. To summarize, multimodal pretext tasks are beneficial, and our approach results in an improved fuse shot and linear probing performance. You can get the dataset and the pre-trained models on our website. Thanks for watching.